Assalamu alaikum. Hi everybody and welcome to this video of showing linear programming of multi-period workforce scheduling problem. This episode is one of the collaborative assignment series for the course Quantitative Methods in Engineering Management and prepared by students Diya, Ahmed and Salim. The idea behind the collaborative assignment came from the instructor of this course, Dr. Laith Hadidi, as a contribution from the Department of Construction Engineering and Management in King Fahd University of Petroleum and Minerals to present solutions of variety problems solved by linear programming through this YouTube channel. In this episode, we will present the following. First, we will give a brief history of the development of linear programming. Then, explain the meaning of linear programming and its objective function. After that, give a glance of the fields where linear programming can be applied to. Then explain the multi-period workforce scheduling problem. And we will display the steps of formulating linear programming by developing a mathematical model to find out the optimum solution for the multi-period workforce scheduling problem. Then we are going to show how to use Microsoft Excel to solve the problem. Now let's talk about the history of linear programming. Actually, linear programming was conceptually developed before World War II by the Soviet mathematician Leonid Kantorovich, who won the Nobel Prize in Economics for advancing the concept of optimal planning. In 1945, an early application of linear programming by Stigler was in the area today called diet problems. A major progress in the field, however, took place in 1947 and later when Danzig developed the solution procedure known as the simplex algorithm. Later in 1984, Karmarkar developed an algorithm that appears to be superior to the simplex method for many very large applications. For more details about linear programming history, you can visit these links. What is a linear programming? It is a method to achieve the best outcome, such as maximum profit or lowest cost, in a mathematical model whose requirements are represented by linear relationships. Linear programming is widely used mathematical modeling technique designed to help managers in planning and decision-making relative to resources allocation. Linear programming is considered, though, a special case of mathematical programming and has a little to do with computer programming. Programming here refers to modeling and solving a problem mathematically. And as we said earlier, and shown in this graph, the relationship of the requirements should be linear and hence represented by straight lines. Linear programming has so many applications that can help in different aspects of life, such as military, where the use of linear programming algorithms helped in solving Air Force stockage problems, such as the design of a mobility kit of repairable. Manufacturing uses linear programming for planning for the optimal mix of products to manufacture a final product. Finance, maximizing return on investment subject to a set of risk constraints, is a popular financial application of linear programming. Marketing. Linear programming models have been used in the advertising aid in selecting an effective media mix. Accounting. A common example of the use of linear programming is to find the optimum mix of products or services that shall lead to maximum profits, while taking into consideration any shortage of resources. Agriculture. Farm planning problems are much more complex. Farmers do not only produce different crops, but have to choose among a variety of ways of producing them. Crop planning may involve choices about varieties, planting dates, fertilizing, and pesticide treatments. Linear programming has proved a very flexible tool for modeling these kinds of complexities. Now we will take an example of linear programming on multi-period workforce scheduling. But first, let's explain what is meant by multi-period workforce scheduling. Workforce is a group of people who work for a particular organization or business. Multi-period workforce scheduling is planning the assignment of people to a job efficiently based on the requirement in different periods. Efficiently means maximum number of people. After explaining the multi-period workforce, we will show the problem now and then apply linear programming on this problem to find the optimum solution. A small firm provides repair service for house appliances. The firm signed a contract with a series of restaurants to provide their services for 5 months. The required service time in hours is given in this table, where it shows, for example, for the first month, they need a service of 6,000 hours. The service firm is assigning 50 skills technicians for this job starting from the first month. 5% of these skilled technicians have to leave monthly to join another assignments and replaced with new hired technicians, but these new technicians will require 50 hours of training from skilled technicians. The salary of skilled technician is $2,000 and work for 160 hours monthly. The new technician got a salary of $1,000 till he completes his training and becomes skilled technician. Now let us formulate the problem into equations and inequalities. First of all, we have to specify the objective of this problem. The objective is to meet the requirement of service hours with minimum technicians, which will lead to minimum cost. So let us symbolize the number of required new hired technicians with X for the month M, and symbolize the number of skilled technicians with Y for the month M. M here is from month 1 to month 5. Now Y and X are called decision variables. To minimize the cost, we need to minimize the total number of new technicians in all months multiplied by their salary, plus the total number of skilled technicians in all months multiplied by their salary. This will give us the following equation. Minimize Z, where Z is representing the objective. 1,000 multiplied by the sum of total number of new technicians plus 2,000 multiplied by the total number of skilled technicians. 1,000 here is the salary of new technician, and 2,000 here is the salary of skilled technician. X3 here, for example, representing the number of new technicians for month 3. Y1 here represent the number of skilled technicians for month 1. Now we will move to the constraints. The first set of constraints in this example is for the time and hours of service required each month. So we will have 5 constraints for 5 months. Another set of constraints will be for the available number of skilled technicians and the shortage in hours due to the number of skilled technicians leaving this job to other jobs. This will introduce another 5 constraints for the 5 months as shown to the right. Last set of constraints is for the non-negativity, of course, for the number of technicians as in the last constraint. Now we will move to Excel formulation and solving this by Microsoft Excel. Now we open Microsoft Excel to solve this problem of multi-period workforce scheduling. First I will explain to you how did we put these functions, the objective function and constraints, in a tabular format, and then we will move later to solver to show you how did we solve it. So first, the objective function here, it is minimize z, which is minimizing the cost. Minimizing the cost, it means minimizing the number of technicians required, new technicians here, and y1 to y5 as skilled technicians, multiplied by their salary, which will give us finally the cost. So the cell here represent this information. We used one Excel function called sum product, which is simply stating the same as in the objective function. You can see here it's multiplying the salary by the number of technicians for each month. For the constraints now, as we explained earlier, we have 3 sets of constraints. The first set of constraints is actually for the minimum requirement or hours requirement for each job, service job, for each month. The second set is for the shortage in technicians, which is we are limited because 5%, as we said, that will be leaving for other jobs. And the third set of constraints is regarding the non-negativity. Now for the first set, which is the minimum hours required, it is here, as we can see, and it is transferred here to the this table using the same function. Here we used a sum product so that we can multiply the coefficients here of these variables, the variables which is the decision variables. As we said, it's the number of new technicians and number of skilled technicians. So we will fill exactly the coefficients here, and then this function, it will give us the final result as it's stated here in the constraint itself. So I'll explain now the first one. The first one, it says that the 160 hours is available for each technician. They can work a month, monthly they can work for 160 hours. Minus, if we are hiring new technicians in that month, they'll require 50 hours of training. So here it says 160 for the number of technicians for Y1, number of technicians it means for month 1, minus 50 hours for the new technician is going to be hired. Now this should be greater than or equal to 6,000 hours, which is as in the contract is the required service hours, and the same is applied to the other constraints. We have for example here the second constraint is 7,000 hours, so we have 160 for Y2 and minus 50 for X2. Now for the second set of constraints, which is the shortage, due to the technicians leaving for other jobs. As we can see here for the first month, and in this one the Y1 available number of technicians is 50, so it is here Y1 is 1, and the right hand side is 50 technicians we have for the first month. For the second month we have 5% leaving, so it will be 0.95 of Y1 because we don't have the full number, 5% leaving, and we have X1 which is the hired now from month 1, and Y2 is moved to the left hand side so that we can keep the right hand side 0. So this is why we find here Y2 as -1. Same is applied again to the other constraints in this set. For the third set, which is the non-negativity, simply it is that we cannot have negative numbers in technicians required. And this set of constraints actually it's going to be added in solver as a constraint. Now we will open solver and then add this objective function and set of constraints and solve. So we will add now the objective, which is to minimize this, and as we explained, this is cell is represented by the multiplication of the salary by the number of technicians, and we'll set it to minimum, and then we'll put here the decision variables. So by changing these variables, number of technicians, and then we will add the constraints. So the first set of constraints is to make this, which is as we explained also, this is the sum product of each variable, decision variable, by the coefficient there here. So as long as these are zeros, then these are not appearing in the function, this constraint. So the -50 here is only for x1, so this will be represented here. So this will be greater than or equal to the right hand side here. So this is the first set of constraints. The other set of constraints is this, to be equal to the right hand side, and the non-negativity, which is going to be the decision variables, is to be greater than or equal 0. Okay, so we have here our objective to minimize, and the decision variables, and the set of constraints. We will be solving this using simplex linear programming, and we will press solve. Okay, now this is the solution using solver, and as we can see here, the numbers changed here to meet the minimization required, and the left hand side now is greater than or equal the required service hours. First is 50, and then the remaining is 0 here. I moved this actually results here, so you can see here for month 1 the number of new technicians will be 0, number of skilled technicians will be 50, and for the second month the number of new technicians will be 8.485, sorry, and the skilled technicians will be 47.5, and so on for the rest of months. So the total cost will be 593,776.51 US dollars. Now this is the minimum cost, but as you can see here that the number of technicians is not integer, and simply we cannot have 0.45 technician to be hired in the second month. So this is actually introducing another method that should be used here, which is a branch and bound. We'll have another video explaining this in this channel later on. So for now, I hope that you now enjoyed and now you got the basic knowledge of using Excel and its add-in solver in solving any linear programming, and you can now simply put any objective function and constraints in a tabular format and easily solve it using solver. This is the objective of this video. I hope that you enjoyed it, and thank you for the time you give us to explain this problem to you. And Assalamu alaikum wa rahmatullahi wa barakatuh.